can find the last forum on our homepage, and also with that, the slides themselves as a PDF, and then all of the SPICE files I use, and just a zip file. If you wanted to play with any of these things, you're more than welcome to. Okay, but may kind of recap what we did last time, is that kind of blocking out the different pieces here. What I'm doing differently here is I'm going to put in the Princeton tone control. I mentioned the one that came with the original kit really didn't do much variation in tone. It did volume, but the tone was very minor. Again, redesigned that. Actually found there was one already done by Fender, so I put that back in. So it's called a common cathode amplifier. It has a gain around 30 or so without a load. Now, a load is when you hook up something like this, and it'll cause the gain to drop a little bit. Sometimes it'll drop a lot. You have to be careful as you interconnect stuff. And then what we'll do is run the simulation of the whole thing. We'll see all the loading effects included. And of course, this will be our tone control and volume control. They're doing just one knob to do both. I think they're just trying to save money when they did the original design. It's easier just to do two separate ones. So it's kind of clever how they played with the R's and C's in there to get bass and treble sound with different positionings of the knob and the volume knob. So it's the two together that give you the same sound effect. Same is true on the Tweed, it did the same thing. And then this is kind of a vacuum tube op amp. Has a gain around 9.5 or so. And most of it's coming from this common cathode amplifier. This is used to give us a boosting in current. And there's a feedback around here, and it roughly goes as 1 plus the resistor ratio. If the gain of the op amp were huge, like an IC op amp, it would be on the order of a couple 100,000. Here we're talking about an open loop gain of around 20 or 30 or so. And then the power supply down here. What's also hooked up here is the filament is also connected to the cathode. That's what this is hooked up here to heat up that to get the electrons moving, and so you get a flow of stuff as you go along. And so that's what we talked about last time. And it's the same schematic now, but putting node numbers on it. And I'm going to run the simulation of the whole system together. And a lot of node numbers last time were just that cut out these pieces and ran them separately without the loading of the next section on it. So we'll see some of the gains will drop a little bit. Also, the kit came with a 45-to-1 transformer, and I want to show you that has an effect on the overall power output. Some discussion about how to change some of those things. And so the input here is actually at node 7, and the output's at node 15, and the input to the op amp is node 4. And when you set the volume all the way to the top here, node 3 and 4 are shorted, and it actually shorts out this R and C. So you get certain sound effects depending on where you put the volume control. And I'll play some music through it. You can maybe better hear the bass and treble in that. A little harder with the guitar to pick out every piece that was there, at least for me. And this is the file that I ran. This I wouldn't run in the student version of PSplice, but we have the full version on the machines downstairs. But I set the volume control to max and the tone to the middle range of it. I also added the resistance. This is the model for the transformer. I added the resistance of the wires that were there. It actually plays an effect in terms of distortion. I run ideal transformers, measured stuff, compared it. When I had tighter modeling, if I want to put this in, I got better results. And then I also included down here is a thing called mutual inductance, and that too plays a role in distortion. I'm a little surprised at that, but with SPICE you can take things out. You can make something perfect. So you measure something, measure the parts, and simulate them and measure the results. And when they don't agree, then I begin to put more modeling and try to get the thing a little bit more refined. And so file these, and these are the models for the tubes that I'm using. So if you're interested, you can. Those are all the things I was running last time. All right. Here, my input was set to. I varied the input until the output just started to distort. I got the volume on full. It was around 44 millivolts peak-to-peak input. And after the common cathode amplifier, I'm getting out about 1.11 volts peak-to-peak. And calculate the ratio of that input to output is about 25. There's also a phase change, so it's a minus 25. Now, without a load, it was around 30, so it lost a little bit there. You can see here I'm getting a little bit of clipping on the bottom of the waveform. So that's about the most signal I can get out before I begin to distort. And then this is the voltage at the output of the amplifier. And if you go back to the input of, or the output of the common cathode amplifier, which is the input of the op amp, you get a gain around 9.55. So that's pretty close to what we had before, 9.65. And the product of these two is the overall gain, with the loading effects included. So I got a gain around 241. I also measured, this was across a 10 ohm resistor, and the reason I used 10, I used a speaker, which speaker's impedance varies from, if you had an 8 ohm speaker, it would vary from maybe 8 ohms to 16 ohms. Depends a little bit on the enclosure. And you kind of get these resonant peaks going up and down depending on how, even the speaker itself in free air. But you don't have really an 8 ohm load, you have something between 8 and 16 ohms. And so I was running this a straight 10 ohm resistor because I had a little bit of a larger one for power. And I measured 1.4 watts out. Surprised, I expected it to be closer to 5 watts before it started to clip. What I did then was I went back and started to calculate the biasing point of the tube, the turns ratio of the transformer, and figured out how I could increase the power by this intersection of AC and DC load lines. I didn't try to write it up because it gets kind of mathematical. But I went in and made the changes based on what I could measure and spice. I was able to get 3.5 watts out of it. And I'm not really at full power out because I could just got to change the biasing a little bit more. I could squeeze out maybe 5 watts. But that's part of the advantage of having a simulation. I actually calculated what transformer I really needed to hook up. And I don't have exactly those windings. This 45 to 1 just came with it. The ones I bought for the kits, you have 4 different windings. So you can try different combinations. But I can calculate which one will give me maybe the overall best results in a maybe 8 to 16 ohm range. For those that are building the amps, I'd like to do a little bit of a lab with you where we play with some of the measurements and see if we can tweak out a little more power. I got about, just did it about an hour before I came here. But that's the advantage of simulation. I'm able to take some of the data that I need to do some of the calculations, and I can calculate what I would need to get it to work. I was surprised that the transformer we picked actually was only giving me about 1.5 watts out. In SPICE, there's a thing that can measure distortion. So this is the second number down here. Total harmonic distortion, the definition will be on the next page, but for that signal, it measured about 0.74%. So just starting to, just on the bottom of it, just start to clip a little bit. I also checked the purity of the input signal. Now in a simulation, you'd think, well, if it's a sine wave, you said it was a sine wave, so it's perfect. Well, actually it isn't because it's doing data points. And so how many data points you specify determines the distortion of the source. If this is comparable to this, then you're not measuring distortion, you got some combination of two. So you need to do more data points and get that smaller if you can. Talk a little bit about this in 302 and 202. Okay, then I took the physical amplifier and did the same thing. The smallest I could set the generator I had at home was 50 millivolts peak to peak. It's just a little bit of clipping on the bottom, although it's still hard to see here. And then I measured, this is the input to the op-amp, or the output of the common cathode. I got about 1.16 volts, and so the ratio of that to the input is about a gain of 23. So it's a little bit smaller than what I had simulated. And then I measured the output back to the input, really where this was measured before, and got a 7.9. I had 9 before. So the product now is a little bit smaller. I was kind of wondering, well, why did that happen? I'll show you in a few more slides why this is a little bit off. We're not exactly the same. I'm using generic models for the tubes. I'm always suspicious whether the specific tube I got is a little bit different. I'm using a data sheet from the 1950s to get the data to do these things, and it could be that it's quite different. I'd like to be able to measure tubes if I can. Dylan's not here, but we were talking about making a curve tracer so we could extract parameters from that. He's got some of the ideas sketched out, and so maybe in our project we could take a look at this semester, maybe next semester. But in the lab we have a little machine, we plug transistors in and we get the curves of them and we can gather the data from there. But for tubes, because you're talking about 300, 400, 500 volts, it's a little different setup. So it's a little bit different, although very similar in what's here. I physically measured then the harmonic distortion, an instrument that's in the 203, 303 lab. And we actually bought another one of these things, and we're going to set up an AEE testing lab in the 303 lab. And so we have this in another instrument to do some measurements. And I want to try to get a lab written this semester, or worse, next semester, so you can have you do some testing on your tube amps when you finish. The total harmonic distortion measurement is extracting the fundamentals. So I had a 1 kilohertz sine wave. I'm going to pull out of that the 1 kilohertz sine wave. And there should be nothing left over, but because the waveform is kind of starting to round and clip, there's other things that are there. This comes from the idea of a Fourier series, that any waveform can be written as a sum of sine waves. They have an infinite series, but really 10, 15 sine waves will get you really close. This is decomposing whatever you give it into its harmonic content. So you had no distortion, these other peaks would be gone. So this is telling me the size of the sine wave I effectively have in a unit called dBVs, decibel volts. So it's showing you that I've got a fundamental of 1 kilohertz, and then in there is a second harmonic, third harmonic, fourth, fifth, sixth, and so on down the line. Okay. And this is actually the waveform. It has like an oscilloscope feature in it too. And then it gave a value of this calculation. So it's given in this unit of dBVs. Whatever you get here, you have 20, and make it the exponent of 10, multiply it by 100%, it's about 3.25%. So it's a little bit higher than what I had come off the simulation with. It's sort of exponential. Once it starts to distort, it just goes up very fast, so it's kind of hard to adjust. I couldn't set exactly the same voltages, and again, I got kind of ballpark models of things. What I'm going to do is overdrive it next, where I'm really distorted, and you can see the two are pretty close to each other. So this is called a dynamic analyzer. It's got a lot of interesting things in it, which is that it can measure this total harmonic distortion. Now, I'll just make a notice here, is that what I've got is multiples of 1 kilohertz. What I'm going to do now is I'm going to just crank the input up until the output horribly distorts. I probably should have done something in between, but I cranked it up. In the simulation, I gave it 200 millivolts as an input instead of 44 millivolts peak to peak. And I got this pretty horrible distortion at the output. It was clipping on the bottom, and I got this kind of a triangle-looking shape on top. But this is what the simulation predicted. So 12.2 volts peak to peak, 13.2. Again, it's similar. It's not identical, but it's similar as to what's happening. And so then I ran the simulation and measured the distortion for that, and found that it was about 37%. And then I measured it on dynamic analyzer, and I got 33.5%. So I'm getting closer as it got more pronounced. But you can see here that the second and third harmonic are almost identical, and almost as strong, and as big as the fundamental. And then the fourth, fifth, sixth, seventh, eight are all about the same size. Now, if you did a transistor amplifier and did the same thing to it, what it would look like, I think I would do it right here. When it's linear, you have a nice sine wave. When you overdrive it, it just chops the top and the bottom. So this is kind of gone. This is kind of gone. And for those that had maybe 202 or are about to get to this probably shortly, is that this looks more like a square wave. And a square wave has just odd harmonics. So it has the fundamental, and then 3, 5, 7, 9, and so on down the line. And you're getting higher frequency tones that are actually pretty large, and so it sounds higher pitched or more treble when you clip it. What you're getting with a tube amplifier that's very different is that this was really the extreme of overdriving it. If you backed off a little bit, what would happen? Let me go back on page 7. This gets more like this, and this gets a little sharper down here. It's sort of like rounded like this. It kind of bends on the top and gets pointy on the bottom when you overdrive it. And that gives you not a square wave, which has these odd harmonics in it, but a waveform that has all the harmonics in it. So it has more content to it, and then that's what sounds different than just being those multiples of odd multiples that are fundamental. Now, there are guitar pedals that are meant to just do that, chop the top and bottom of the waveform off and create these higher order harmonics. The fuzz face is one. And so you get this real screechy noise when you're playing a note because you're getting the things out to 7 kilohertz, 9 kilohertz, 11 kilohertz that have a fairly large amplitude. It's very, screechy kind of sound. But that's why a tube sounds different. When you overdrive it, it doesn't clip. Like if you look here, it clipped on the bottom, but the fact that it left this here gives me still that, you can see the harmonic content is still even and odds together. So that's what makes that sound different. Then I started thinking about the sound effects. And we mentioned, people told me when they play guitar that the tubes respond when they overdrive them. But I wasn't sure, I didn't think that was really modeled in the tube, but then I thought about this case here. So I ran the simulation. I tried to do it in lab, and I watched the power supply changing a little bit, but I didn't get the setup that I wanted to. So I went back and did simulation. I took this waveform, and I delayed it for about 8 seconds, and then I hit the amplifier with it. And all of a sudden, I saw the output shoot up, and a second later, or almost 2 seconds later, become this wave shape. So what was happening, I'll go back to the first page here. The voltage across this diode is pretty large, and so if you drew more current for the load, then you draw more current through the diode and you drop more voltage here. And I watched this voltage go from 220 volts to 150 volts. And then it would recover after that waveform went away. But it takes several seconds for it to recover. And so that's going to cause these amplifiers to have different voltages at their to running them. And the gain of the amplifier changes with the power supply. So I changed the power supply by 10%, and the gain changed by 7%. So it's almost like a 1-to-1 ratio. But I didn't do the case from going from 220 to 150 volts at this node. But it took several seconds for it to respond, because you have these large capacitors here, and you get what's called an RC time constant. That may be what you're hearing. I don't know, I need to do more testing on it. But again, what I'm seeing is harmonic content that is everything, the even and the odds together. And that's going to give you a fuller sound. And the transformer actually also has distortion. I did one test some years ago on the Tweed, and I have a simulation of that one too. And I didn't include the mutual inductance for the transformer, for those who know what that is, and the losses in the coils. And I got a result that was pretty close, but when I included that, it almost was identical. Because I had that model pretty tight. I measured all the components in that Tweed that's in that box. This one here, I had measured everything, and when I wrote this up, I was doing pretty close modeling, but then I bumped the tube and I cracked it, the power supply tube. This one here. And I ran out of fuses, so I was putting fuses in the instruments to give back to people, and so I put a slow pull fuse in here. And I turned around after I bumped it, and this was almost on fire. It had smoke all over it, was coming out. What had happened, this thing broke the vacuum, and now it was drawing huge amounts of current. The slow blow fuse, I don't remember the exact number, but it's like if you have like a 2 amp fuse, it'll let like 4 amps go through for a while. It might double the current for a while before it responds. It might be like 30 seconds, but that was enough to get this thing to literally almost catch on fire. The whole thing was billowing smoke. So I replaced that, and it's not exactly the same transformer, and maybe that's why I'm off by a little bit, because I measured everything here when I was doing the simulations, but it kind of destroyed my sample. So I go back to square one to remeasure this and see if I can get closer to agreement. Because I eventually measured the power supply. Well, it's actually the next thing to talk about. These are just sequential pages of the last talk. What I want to do next is show you how the tone control works. Not the mathematics, we're just testing it. Now, when SPICE finds models for things, it does a series of operations. And so to get this thing to do a phasor analysis, which is really called a Bode plot, a plot of magnitude angle versus frequency, what the program does is it sets all AC sources equal to 0 and does some calculations for DC biasing. Well, if you do that with a power supply, you don't get the power supply voltages out. So what I had to do was put the DC voltages here that this power supply creates, and then let SPICE deal with the amplifier and find this AC model from its DC parameters. And so I had to go measure the average value of these 3 node voltages. The first one's got more ripple, I mentioned last time, the second has less, the third has less. But when I measured the power supply that I have, the voltages are a little bit lower, they're about 10% lower. So that's why my gain is, I think, a little bit lower than what I was seeing in the simulation, because the voltages I have for my actual amplifier aren't the same as this. And that would lower my operating voltages, it gives me less gain for the tubes, and so that would account for some of the reason that they're not exactly the same. I took these voltages in the simulation and then hooked them up. And then ran the simulation a couple times. I originally set the volume control to max and tone control to mid, and then I replaced the stuff that was there for the power supply with the average value of those 3 nodes coming into the circuit. Then you can sketch magnitude, angle versus frequency. And so this was the one with the volume maximum and tone in the mid position. It pretty much gave me the audio band from about 46 hertz to about 40 kilohertz, and a gain of around 243. So it matches the simulation we had before. I was doing time domain simulation, now I'm doing frequency domain. And then I started to change the positioning of the pots, and so I ran it again. I put it in the bass position, and then I ran it. You can see I've got more gain for the bass tones and less for the treble tones. And then I ran it again. The tone max and the volume max, it got the same results. I just got a straight amplifier with no tone control showing up. And so if you don't really want to use the tone control, you can set these to a point where you pretty much just have a straight amplifier. But if you want to have, some changing effects, I want to putting the tone at max here and the volume control at about a third of the distance. It's a logarithmic called audio taper. You can see here I've got more treble than I've got bass tones. So the circuit's doing what I would think it's supposed to do. And I did the same thing for the previous circuit. It didn't come close to this. The next thing to do is to start to analyze the circuit, figure out how things work. If you're in 202, there's a supplemental problem where I do a tone control, figuring out a bass and a treble. Not this circuit, but a different one. But the methodology's in the course, so you can do that kind of calculation. And lastly, I put it way down to 1/10. And you can see it's very much treble and very little bass. Then I also have another instrument I've been using, measure Bode plots and also distortion and power versus distortion, using this HP audio analyzer. I bought one about a year ago, and then I bought another one for the lab. So we have this also up in 303 as part of an audio testing lab that we're put together for AEE. And you can get these Bode plots out from that instrument. And you can see here, well, what this machine does is it normalizes the gain at 1 kilohertz to be a gain of 0 dB, which is a gain of 1. If you compare these data points with the analyzer, which has normalized this, they're fairly close. This one says it's about -8 dB, it's about -10 here. And then at 10 kilohertz, I got 6.8, and 10 is over here, so maybe it's around 7 or so. But what I was surprised to see was that in the simulation, it rolled off once I got out to 40 kilohertz or so. But in the actual amplifier, I saw this peak occurring. And that's not uncommon to see in amplifiers that at higher frequencies, there's more gain. And sometimes there's too much gain, and you actually get a little oscillation. It's giving gain to the noise that's present in the circuit, and you get some oscillation or ringing on the output. Now, you can't hear that. Well, this one, you might hear a hiss in the speaker, but when it goes farther out, you can't hear it, but it's dumping power into the speakers. The amplifier is giving up the power to heat up a little bit more. And so getting rid of that's important. Where this is coming from, because I modeled the tubes pretty carefully, this is the transformer that's out. I just have an inductor and a resistor in the model, but there is some capacitance, and it resonates with that inductor, and I'm guessing that's probably where that's coming from. So the next thing I want to look at is measure the transformer, but measure it out at higher frequencies and see whether include some more stuff in the model. I know that others have done this and stuff some capacitance. And I'm trying to get the simulation and the models to agree. So I can do design changes, even just by running simulations and seeing what happens, and then I can order parts or make decisions in labs, other than just going in there and soldering and unsoldering everything. But this audio analyzer will be part of the tools that we'll have in lab. The dynamic analyzer also will be the special separate station in the far left-hand corner as you come into the lab. We're going to use that to test our amplifiers. And we'll add more equipment as we can afford to do that. We have some money from the college and from the department, and then we can also be doing some fundraising to that too. But I'd like to have a testing lab and show you how to take some measurements. For those that haven't gotten that far in the curriculum and would like to get some information about your own amplifier and see how good it performs. Or if you want to modify it, we can talk about that. Okay, let me show you what that sounds like. So again, I've got the 12-inch speaker in here. Got the amplifier set to mid-range. Got the CD player for that as kind of beat up here. So that's in the middle. So that's all the way to bass. It goes down with the bass rate. All the way to treble. But you can hear the tone changes with the positioning back and forth. Now also what I added in here was a second input plug and did a resistive adder so that I added the right and left channel, so you could use this as a guitar amp if you wanted to, playing 2 guitars, or you could hook it in the right and left channel and then be able to play, a CD player or MP3 player or iPod or whatever you have to hook up in there. So again, it's about a 5-watt amplifier. Again, you tweak a few things like the transformer and the biasing on it. But it's one of the projects that we're doing. We have 4 people doing them. We've got more kits if people want to start one yet. We've still got some more in inventory. But it's one of the projects that we've been doing for a couple years. So, a simple amplifier and it's really decent sound. Any questions about the amp or stuff to do? Yeah.
Well, okay. I may have missed something. Is your tone control in here? I mean, hearing it now, it sounds like a treble boost. Is that really what it's doing, or is it already subtracted for the mid-range and then?
It actually is giving you quite a bit of gain for treble. It's attenuating the bass, basically. And so it's giving you the gain you had before, but I'm actually lowering the bass tones. So that volume control is playing with the 2 potentiometers, essentially changing the resistive path seen by the input and output signal, shorting, opening, different frequencies, so you can get more bass, less treble, but the gain's still roughly the same. But the gain I had for the flat band one, just moving one end down or the other one up, just through measurement. And again, you can learn to calculate these things and actually predict the exact same results.
I'm just trying to think about if you were to totally take that whole tone aspect out of the circuit, would it be how it sounds? Would it be the volume it was when you had the tone cranked all the way this way, except that it would be flat?
I didn't crank it all the way up because I got the CD player on minimum,
right?
And so it was still kind of loud. But
I mean just the tone now. Like when you had it all the way to one side, it was very high pitched.
Yeah, it would be. Well, it's like in the sort of the middle position. You pretty much have somewhat of a flat response.
Right.
So you get almost as if there was no tone control at all. So you could, if you didn't want a tone control when you're playing, just leave it in the center position roughly. And then you play with the volume, and pretty much you get a wide bandwidth result. But again, you could simulate that and see exactly what you have, where you could measure it with the instruments in different positions. I ran a lot of curves, just did a few up here to show, but the overall gain is no more than 240 or so that we saw. You're just taking one end or the other, just basically reducing it. So that's why it sounds more treble or more bass. I'm just taking one part, just attenuating the other side of it.
So are you losing output power by including the tone portion?
It would be, yeah, because you got, well, I was measuring power at like 1 frequency, but now you've got all the frequencies there, so yeah, you got a smaller signal. But then you have more of that the treble, so it's going to be giving that power for that range, and so that's why it's sounding louder. Yeah, the other ones?
Is anyone bypassing that circuit? Who's building these? Is there?
Not really, although the original tone control didn't do anything, so it was like it was bypassed. So it's just a straight amplifier, so we're just giving you the audio band. But actually, that one curve where it's flat, the one that's before this one, the first one, that's really the full amplifier's bandwidth, as if the tone control weren't there.
If it was like exactly in the middle.
Yeah, right. Just give you, and you turn the volume almost all the way up. You kind of short out one of those capacitors, and you pretty much get a flat response on it. And the tweed's very similar. They use 2 volume controls and 1 tone control. But it's a very similar type of a circuit. The tweed is really the champ twice. They just kind of fold it over. And this is like a 4-watt amplifier. And so what you would get is twice the voltage out, so you get 4 times the power. So roughly 4 times what this is what this will be. Okay, great, thank you.